Okay, so we are finishing our notes for section 3.5. We're looking at the Gaussian model. We're actually looking at problem number 5. Is that right on your gift? Okay, and so can you help me out here? What is the equation? Because I don't have a gift in front of me. Type it in. So this is y equals 0.0399 times e to the opposite of x minus 74, close parentheses, squared over 114, and we want that between 30 and 110. Thank you. So go ahead and enter that in your calculator. That is 0.0399. Yep, and then e to the times e to the, I need a fraction template, an opposite, and a parentheses, and x, is it x minus 74? Quantity squared over 114. Does that look okay? Yes? Calculator. Does it look like a straight line? Everybody else has a calculator? Yes? Yes. Okay. Okay, so since you're pushing, I have to graph it again. It sure looks like a straight line to me also, a horizontal line. But I think if we mess around with the window, let's go menu, window zoom, window settings. They did tell us that the x is supposed to be between 30 and 110. Is that correct? So let's make x minimum 30, x maximum 110. Still looking like a horizontal line. So I think if you look back at the picture on page 261, what do you notice about the y-axis where it says distribution? It's really tiny. We're like way between 0 and 1. We're between 0 and like 0.05 or something like that. Let's try shrinking this y coordinate down. So I'm going to go menu, window zoom, window settings, and I'm going to go to y minimum. Oopsie. I'm going to make y minimum 0, but I'm going to make the y maximum like 0.01. Well, that was too small because now that bell-shaped curve is off my screen. So let's change that. Menu, window zoom, window settings. How about making that like 0.05? That looks better. Are you getting a bell-shaped curve on your calculator? All right. So now at this point, we want to know what it, where's this maximum occurring? So we go menu, analyze graph, maximum, right? And now it's saying, well, where do you want your lower bound? I got to get to the left of that bell, and then upper bound, I got to get to the right. And I click, and it sure looks like it gets the order pair 74, comma 0.04. So what was the average? Is it average test score that we're looking for? So what was the average test score? 74%. 74%. Are we okay with this? Yeah. Questions on this? All right, let's move on. Yes. Gotta go. Okay. All right, we'll continue the video. Okay, let's take a look at some logistic growth models. Some populations initially have rapid growth followed by a declining rate of growth. So I drew the logistic growth model.
Good afternoon.
Here.
At this time, all students in track and field have been dismissed.
So here is where this function will have a rapid growth right here, and then it's going to have a declining rate of growth here. All right. This is the logistics growth curve, and it's also called a sigmoidal curve, in case you were interested in that. Let's take a look at an example of a logistic growth curve, and that would be number 6 from your gift. It says on a college campus of 7,500 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this equation, where t is greater than or equal to 0, y is the total number of students affected by this virus, and t is the number of days. The college is going to cancel classes when 30% or more of the students are infected. So how many students will be infected after 4 days, and after how many days will the college be forced to cancel classes? Let's start with part A. How many students will be infected after 4 days? What are we going to do to find that answer? Elliot. Okay, so you're going to use your calculator. You're plugging in 4 for t. All right, and what did you get for your answer?
36.4.
So, maybe about 36 students were infected after 4 days. Everybody agree? Okay, so now after how many days will the college cancel classes? How are we going to answer that? Sarah?
You have to find out how many students population.
Okay, so we want 30% of the student population, so 30% of 7,500, that's 0.3 times 7,500, and that turns out to be what?
2,250.
2,250. And now, Sarah, you said you're going to plug that in for y? Yes. For the number of infected students. So if I plug that in right here for y, I would get 2,250 equals 7,500 over 1 plus 7,499 times e to the negative 0.9 t. Does that look okay? All right, at this point, I personally would probably write this 2,250 over 1, and then I would cross multiply. So if I write that over 1 and I want to cross multiply, 1 times 7,500 is going to be 7,500, and then I've got 2,250 times this denominator, 1 plus 7,499 times e to the negative 0.9 t. Does that look okay? What's going to be our next step in solving? What should we do next? Aaron? We could distribute the 2,250. That would be fine. Or we could do what else? Instead of distributing, we're definitely going to have to rewrite in ln form, but let's wait until we get just e to some power by itself. So can we get rid of this 2250 somehow? All right, let's do that. Let's divide by 2,250 to both sides. And then when those divide out here, what is 7,500 divided by 2,250? 10 over 3. All right, so that reduces to 10 over 3 equals 1 plus 7,499 times e to the negative 0.9 t. Does that look okay? All right, we're still trying to solve for e. What's going to be our next step, Emma? 1 plus 12 to the basic e. Well, we're trying to solve for t, and we've got e raised to some power that we really can't touch yet until we get that by itself. So I think we got to get rid of the 7,499, and we also have to get rid of the 1. So what should we subtract? Well, the 7,499 is being multiplied by those. Yeah, let's subtract 1 from both sides. So what's 10/3 minus 1? That's 10/3 minus 3/3, 7/3. So I really get 7/3 equals 7,499 times e to the negative 0.9. What should be our next step here, Mary Grace? All right, now we're ready to divide by 7,499. And when we do that, we end up getting what on the left side of our equation? 3 zeros and a what? 311. Are we okay with this? Equaling e to the negative 0.9 t. Is that what it is? Now, Aaron, you were suggesting a course of action at this point. What are we going to need to do? Okay, so what should I write? Do people agree with that? And you know, if you don't want to jump right to the ln and you want to write it as log to the base e of 0.000311 equaling negative 0.9, you can certainly write it this way first and then write it this way. That's fine. Whatever works for you. And then at this point, we're still trying to solve for t. Sarah, you.
You wanna try besides that, maybe.
All right, dividing both sides by negative 0.9. And that's going to give us the number of, here's our value for t. 8.97. So is that approximately 9? 9 what? 9 days. So pretty amazing that after 4 days there were 36 students affected. And after 9 days, there were 2,250 students affected, right? Okay. Questions on this? But remember, if you're thinking about what the graph is going to look like, so I have horizontal asymptote, and right now we're in that rising area. It's rising really quickly, the number of infected cases. But it's going to have to level off because there's only 7,500 students in school, right? So I would imagine that this horizontal asymptote here will be y equals 7,500. And this will be y equals 0. Does that make sense? Okay, let's switch topics and talk about logarithmic functions. And in particular, let's talk about earthquakes. On the Richter scale, the magnitude R of an earthquake of intensity I is given by this formula. R equals log of I divided by I sub 0. I represents the measure of wave energy, and I sub 0 is the minimum intensity used for comparison. So for our purposes, we're just going to, anytime we see this formula, we're going to replace I sub 0 with 1. We're just going to use 1 for I sub 0. Okay? So this example here is not on your gift. So can you get this down on your notes, please? This one says, find the intensity per unit of area for each earthquake. All right. There was a really strong earthquake in 2004 in northern Sumatra, and the Richter scale rating was 9.0, which is a really rare, very powerful earthquake. So how are we going to find the intensity of that earthquake? We're going to have to do what? What is that? What's that? Using your voice. We're going to replace R with 9. I think it's what makes it work. All right, so we're going to plug in, here's our equation. We're going to plug in 9 for R. So I get 9 equals log of I over 1. I don't have to write the over 1, right? So I just have this equation to solve. 9 equals log I. So now how do we solve for this intensity? How do we solve this equation for I? Yeah. Stephen, I don't see a base here. So what base would this be understood to be? All right, so if I have a base 10 here, now what am I going to do to solve for I?
You're gonna rewrite it.
How so? What's going to look like?
And
You're going to rewrite an exponential form?
yeah,
All right, so what to the what equals what?
10 to the 9 equals that.
10 to the 9th equals I. Do people agree with that? All right, and 10 to the 9th, isn't that a 1 with like 9 zeros after it? Does that sound right? Oh, let's see. Let's slide this down. Give myself a little room here. Drag. Okay, so really, for this problem, part A, the intensity is really a 1 with 9 zeros after it. So the wave intensity of this earthquake was 1, what? What do we call this? 1 billion, right? 1 billion. Okay, so what about comparing it to another 2004 earthquake in Alaska? This one had a Richter scale rating of 6.8. So would you take a minute to figure out the intensity of this earthquake in Alaska? How should we set this one up, Logan?
So you set it up, you've got to replace R with 6.8.
So, okay, so we're gonna have 6.8 equals log I, and then what?
Log is to the base 10, so I rewrote it as exponential form.
Okay,
And
which
you
is
got 10 to the 6.8 power equals I.
10 to the 6.8 is equal to I. All right, and when you do that on your calculator, I turns out to equal what? 309,000? 570? Do people agree with this? That look okay? All right, questions on this? That brings up your last example from your gift. This time we're going the other direction. In this case, I'm giving you the intensity, and I want to know what would be the Richter scale number. All right, so in this case, if the intensity is 68,400,000, I'm still using this formula. Remember, it's really I over I sub 0, but we're just using 1 for that, so we don't need to have all that. So we can just say R equals, whoopsie, R equals log I. So how am I going to find the magnitude of the Richter? Find magnitude R of the earthquake, Alex. R equals are we on the first one? Okay. And on your calculator, Alex, what's it? Are we using base 10 for this? All right, let's come round to the nearest 10. So 7.8 on, is that right? 7.8 on the Richter scale? Okay, and so that's for part A, and then for part B, we would want to do the same thing, except we want the log of 42,275,000. Are we okay with this? Okay? And what does this one turn out to be?
Yeah, but
7.6. So the Richter scale rating for this one will be 7.6.
how well do we have to know what we?
Oh,
That's a great question.
I think that is a great question. If you're asking, do we need to memorize these formulas? My answer is no.
If I give you an earthquake problem, I'll give you this much. If I give you a, a logistics growth issue where there's this virus going on at college campus, I will give you that formula, you can see what to do.
Okay, so you just have to know how to put it.
Yes, however, I think you should count on a fruit fly problem or something like it where you're gonna have to write your own model, right?
And that is the case, we did that problem last class. If I say the fruit flies are growing according to the law of exponential growth, whatever the phrase would be, I will probably remind you of that formula like this, but you're gonna have to find the A and the B. Does that make sense?
Yeah.
Same thing if I give you, this is exponential growth, same thing if I give you a half-life problem, I will probably remind you, I'm sure I will remind you, that the formula that you will want to use, that is y equals a times e to the opposite of b times x. Again, I'm gonna give you the half-life, and maybe I'll give you the initial amount, and ask, well, how much is gonna be left after this many years? Or, if there's this much left, how many years have passed? I can ask both ways. Or some of the, obviously more complicated ones, but the ones we can talk about in homework, they don't give you the initial amount or the b-value. They tell you the half-life, right? And then they say, well, after 1,000 years, 3.6 grams a week. So that's a little bit trickier because you don't know what to put here, and that's when we talked about this last class, that you would say, well, I'm gonna have to make up an initial amount, like 100 grams or 100%, right? And then say, oh, after that half-life period, the amount remaining would be down to 50. So I would then fill in, let's say the half-life was 5,200 years. I would say, okay, my 100 grams or my 100% is going to be down to 50 grams or 50% after that many years. And then use that to solve for B. Does that make sense? So in that case, I'm not really giving you the model. You got to come up with your own model. Does that make sense? Okay. All right, that's it for my notes. Now it's the time for you to ask questions on this homework. You did lots of problems from section 3.5. I am.
Shout out to my boy Harmon. Bye, Harmon, Claire. See you, Harmon.
All right,
Bye, Claire.
thanks for watching.
Bye, Claire.
Let's see.